Good evening. This is a little better? Yes. Okay, that even blew my ears. But it did get everybody's attention. On behalf of Marcia Landholt, the Dean of the Graduate School, it's my pleasure to welcome you to the Walker Ames Lecture tonight. It really is extremely pleasing to see so many school kids out here this evening, and I'm sure you're really going to enjoy this talk. The program began actually in about 1936, and support for these speakers to visit the campus and to spend a couple of days here visiting with students and lecturing. The support came from a fund established from a bequest from the estates of Maud Walker Ames and her husband, Edmund Gardner Ames. To date, we've invited over 300 speakers to visit the campus under the sponsorship of the program. We should thank Janet Jones, who's made the arrangements for tonight's talk, and also the members of the selection committee who did really an outstanding job in identifying this evening's speaker. The program tonight, which is really the reason that you're here, the program tonight addresses issues that occupy the forefront of human imagination. Professor Craig Hogan, who is a chair of the University of Washington Department of Astronomy, will give you a specific introduction of tonight's speaker and topic. But just a little bit of a commercial message here. Given your interest in things cosmic, I think you'd appreciate knowing that Craig himself has just finished a book entitled The Little Book of the Big Bang. And this book will be available through Copernicus Press at bookstores in March. Okay? It answers questions most often put to him about the origin of the universe, and I'm sure that it's a book that you would enjoy. And for the school kids in the audience, I'm sure it's a book that their teachers would enjoy your reading. Thanks very much.
I didn't expect that. Thank you. Thanks, John. He hasn't even read it. It's good. So I hope everybody has a seat. I know we have a lot of people here tonight, which is delightful. There are a few more still in the front section, if is anybody still standing. Isaac Newton, the founder of modern physics and astronomy, in a rare moment of public humility, quoted the following ancient text. He said, "If I have seen farther than other men, it is because I stood on the shoulders of giants." This famous remark applies to our speaker tonight, both literally and metaphorically. As the director of the Space Telescope Science Institute, Bob Williams has very literally seen farther than anyone has before. He has brought before the eyes of the world images of the first galaxies to form in our universe, images carried by light that has been traveling through space since before our own planet condensed out of primordial gas. But Newton's remark also applies to Bob in the sense that Newton intended. Bob is a scientist famous for his deep insight and his broad vision. This is, of course, why we invited him to speak here tonight, not just because of the pretty pictures. Bob's astronomy career began in middle school in a class back in California back in the 50s. Astonished to learn about the existence of planets, other planets, not Earth, he embarked on his first project in deep imaging. He set about searching for life on Mars by examining a picture in a school pamphlet with a magnifying glass. And like the pictures he takes today, it had lots of dots in it. You'll see some of those a little later. He attended Berkeley and then the University of Wisconsin, where he received his PhD in 1965. He was on the faculty of the Stewart Observatory at the University of Arizona for many years, then moved to Chile, where he served as director of the Cerro Inter-American Observatory, which is the main American observatory in the Southern Hemisphere, from 1985 to 1993. In 1993, he was appointed the director of the Space Telescope Science Institute. We're very pleased to have him here in Seattle, and tonight he will talk to us about probing the universe with the Hubble Space Telescope. Please join me in welcoming Professor Robert Williams.
Thank you. I am delighted to be here in Seattle tonight, addressing you about one of my favorite topics, which is Hubble Space Telescope. It certainly is an honor for me to have been asked to serve as the Walker Ames Professor this week, which is the reason, as Professor Hogan mentioned to you, that I'm visiting the campus. You should realize that the Department of Astronomy here at the university is really a very distinguished department, and that has a lot of involvement in Hubble Space Telescope. There are people from this department, well, certainly a large number of them, who use the telescope. Several of them have been involved in the construction of the instruments that have been on the telescope. And in fact, one member, Professor Bruce Margon, former chairman of the department before Professor Hogan, is actually chair of the board of directors that oversees our institute. So in fact, there is not just a lot of involvement in the program of Hubble Space Telescope that emanates out of the University of Washington, but a number of significant results, both from that telescope and from other telescopes, have come from this distinguished department. Well, I'm here to talk to you about the Hubble, and what I hope to accomplish in the next hour is to tell you something about the development of the telescope, then describe the servicing missions, particularly the first servicing mission that was so important in getting the telescope to function as it now functions, and then spend the rest of the time talking about the excellent science that is coming out of the Hubble. Let me begin by telling you something about the science of astronomy. There have been two great scientific revolutions in human history. The first was the Copernican revolution, the second has been the Darwinian revolution. The Copernican, and both of them have had a profound effect on mankind and the way that we perceive of ourselves. The Copernican revolution began in the 16th century and served to remove the Earth from the center of the solar system where Aristotle and the Greeks had placed it 20 centuries previously. For 2,000 years, mankind believed that the Earth was the center of the universe. Few people could have realized when Copernicus first suggested, upon trying to explain the motion of the planets in the skies, that it was more straightforward to explain them by putting the sun at the center of the solar system. Few people would have realized the profound effect that one suggestion has had on mankind, because it removed the Earth from the special place that it had had for 2,000 years. The roots of this revolution lay in the detailed measurements that a few astronomers working in isolation, not knowing about each other's existence, that they made in charting the motions of the planets. The Copernican revolution really was a tough play. It took several centuries to be consummated. One of the major religions in the world was against it. People who believed in it were put on trial and condemned to death. But eventually, it was accepted because the facts in favor of it were overwhelming. But after that time, mankind perceived of itself, ourselves, in a completely different way. The second great scientific revolution, the Darwinian revolution, began in the last century. Darwinianism has taught us that the human species did not evolve or develop in isolation from the rest of the animal kingdom, but in fact evolved from it through a process that is called natural selection, or survival of the fittest. And that, in fact, the human species, the state that we have arrived at, is the product of a long chain of evolution. Like the Copernican revolution, the Darwinian revolution has also had a tough play. I dare say that, generally speaking, if I address an audience of this size, one will find that there are a certain group of people in the audience who do not accept the Darwinian revolution. Judging from our experience with the Copernican revolution, I suspect it's going to take some time, another century perhaps, before the Darwinian revolution is accepted with the universality that the Copernican revolution has been accepted. But eventually, most of we scientists are convinced that that will take place. So Copernican revolution took Earth from its special place. Darwinian revolution has taken mankind from what was believed to be its special place. And in this sense has really had, these concepts have had a profound effect upon the way we perceive of ourselves. If one defines scientific revolution to be the struggle that society has in coming to grips with scientific fact, then I think that one can argue that we have just entered a third great scientific revolution. One, in this case, that is not based on the physical sciences, but on the biological sciences. It is what I call the genetic revolution. Our ability now to alter human characteristics in situ by genetic manipulation, I believe will lead to a revolution that is as profound as the Copernican revolution and the Darwinian revolutions have been in their time. In fact, witness already just the debate in the past year, now that the Dolly, the sheep, has been cloned, the tremendous ethical debate that has commenced in our society that was preceded by a debate over abortion that is different, but I think related to that. And one can understand, in fact, the earth-shaking implications that new technology is bringing to us. Again, based on our experience with the Copernican and Darwinian revolutions, I suspect that it will take several centuries for this genetic scientific revolution to be consummated. Arguably, one could say that it began in the 1950s, about the time that Watson and Crick deciphered the double helical structure of DNA, and is going to take its course depending upon those discoveries that are related to genetics, biological evolution. And it is difficult to say at this point exactly what the consequences of that will be and how it will run its course. But again, based on our experience with the previous two revolutions, where people were actually put to death for their belief in ideas that were unpopular, not yet accepted at that time, I suspect that it is going to be a very difficult play. But at the end of it, I am convinced, whichever way it goes, that we will come to a much better understanding of what life is, what it means. I wish I would be here to enjoy that knowledge, but I'm sure it's going to be centuries from now before that takes place. Well, we're not here to talk about that, as interesting as it is. We're here to talk about the science of astronomy, which was at the core of the first scientific revolution. And so let us, from now on, confine our attention to astronomy and to the great results that Hubble Space Telescope has given us. Let me preface my remarks by saying astronomy is what we call a pure science. It doesn't really produce any marketable quantities. Lots of marketable quantities that are associated with science. All you have to do is take a magazine like Astronomy or Sky and Telescope and open up and see all those advertisements for telescopes. So there's hardware associated with it, but the fact is astronomy itself doesn't really exist to provide us with a better mousetraps or things that directly affect our life. The products of a pure science like astronomy are ideas. They are concepts. They are satisfaction of curiosity about our global environment. And it's interesting. We live at a time when that seems to be underappreciated, because one of the questions that I get asked most frequently is, well, why are you doing this? Is it worth it? Hubble Space Telescope costs a lot of money. You know, do you think that we should spend money to that? My answer is, well, I have many answers. One of them is that depends upon you, the citizen who funds these things. But look at the historical record. Look at the fundamental way in which we perceive of ourselves differently because of the Copernican revolution. I tell you, pure science, and particularly astronomy, has a profound impact on the way we perceive of ourselves and our environment. And I'm going to try to bring that out in some of the images that I show you that are coming from the telescope. Hubble Space Telescope is, at the current time, arguably the premier instrument in use in astronomy, and there are many other fine ones, that is revealing the nature of the universe to us. It has had a dramatic impact on the science of astronomy in the past 5 years. And again, I hope that you will come to understand and appreciate that better after we're through showing you some of these images. So let me tell you about Hubble Space Telescope. There's one important fact about Hubble. It's up there. It's not on the ground. It's in space. It's not easy to put a large device like that in space. It takes a great deal of effort, manpower, and money. And it's up there for one reason. The Earth's atmosphere is great for sustaining life on Earth, right? Got to breathe it. But it does bad things for the radiation that we study from distant objects. It absorbs that radiation, completely blocks out X-rays, a good part of the infrared, gamma rays. And even the optical, which it lets through, after all, we can see each other. We see starlight, we see the sun. It distorts the light and prevents us from achieving really excellent focus on images of the objects that we like to see. So ever since the payloads of rockets became large enough for us to think of launching something into space, astronomers have wanted to do just that. That occurred about the time of World War II, or rocket payloads, or the development of the rocket, of course, goes back to Chinese times, goes back many centuries, but the art was not really developed. It depended on so many things due upon warfare, unfortunately. Not one of the better aspects of human culture, but such is the case. It was after World War II where the development of rockets led to a situation where payloads were large enough that one could think of putting a telescope in orbit. There was a seminal paper written by a colleague of those of us in astronomy, Lyman Spitzer, a Princeton professor who recently passed away. In 1946, I believe it was, a prescient paper, far ahead of its time, where he suggested the advantage, well, first of all, he suggested that a large space telescope be constructed, or a space telescope, multi-purpose, be constructed, put in a rocket, and flown. It was really not possible to do it at that time, and therefore the paper was was not paid much attention to and forgotten until, in fact, the time of the manned spaceflight program of NASA and the development of Space Shuttle. And the reason for that is any multi-purpose device is going to suffer failures, have breakdowns, and needs to be serviced. And it wasn't until the shuttle enabled us to basically have a space transportation system that led to the feasibility of thinking that one could put something up there that's complicated. Otherwise, you're really left to putting up very simple payloads with smaller mission lifetimes. Hubble Space Telescope, initially called simply the Large Space Telescope, was a project that was proposed by astronomers to NASA. It was studied by the National Science Foundation. It was recommended as a project to NASA. It was put to Congress. It was debated. They bought off on it, and it was funded and eventually developed. Eventually, it was named after American astronomer Edwin Hubble, an American astronomer who made important contributions to our understanding of the expanding universe. And so that basically is the story of how Hubble Space Telescope came to be. Let me start with the first slide here in showing you a mock-up of the telescope. That is a drawing of Hubble Space Telescope. It is the largest piece of equipment, basically, that will fit in the bay of the shuttle. And that is what dictated its size. It actually is very common to the ground-based telescopes that are proliferating here on the surface of the Earth, in the sense that the core of the telescope is a large primary mirror. I say large. In fact, it is not large anymore by ground-based telescope standards, since we have ground-based mirrors that are 10 meters in size. This is 2.5 meters. It's not quite 10 feet. Concave mirror that accepts light from distant objects and brings them to a focus by bouncing the light off what's called a secondary mirror that is up here at the top end of the telescope, put in place there, maintained in place by some struts that you see here. And the reason I call attention to those is because incoming light scatters off these struts, and it is these structures that produce that X-shaped or cross-shaped pattern on bright stars. The light is reflected down through a hole in the primary mirror of the telescope. You see a very large light baffle here that acts to keep out stray light, and then is brought to a focus down here in this gaggle of instruments that you can see relative to the size of a human have the size and shape of a telephone booth. There are also some instruments up here behind the mirror that also make measurements. They're instruments that image the light. And in fact, most of the images, the photos that I'm going to show you were taken by, in fact, it is right here. This particular device here was called the wide field camera. In any event, there are any number of measurements that the telescope can make. Only one object can be measured with one instrument at a time, but a number of these instruments can be operated in parallel, either taking photographs or taking spectral measurements of objects that are very close together in the sky. The telescope weighs 11 metric tons, and that's a lot of mass, 42 feet, about 13 meters from front to back. So it is really a very large, complicated piece of equipment. It is surrounded by all sorts of things: data recorders, gyroscopes, central processing unit to store the data, transmitters. There are some solar arrays also on the telescope. And it was launched on board Discovery in April of 1990 with a crew of astronauts who were sent up on a mission whose sole purpose was to deploy the telescope. I should say that the cost of the telescope to this point, which is almost 8 years after launch, has been about $3.5 billion. It is an expensive project, one of the largest scientific projects currently underway in the world. And what can I say other than that's a lot of money. But when you compare it to other things like the construction of dams or aircraft carriers or whatever, it doesn't stand out in that sense. But there's no question that this is an expensive project. Well, this shows a schematic of how the telescope gathers the data and sends it down to the ground and over to our institute in Baltimore, which together with Goddard Space Flight Center operates the telescope. Basically, light comes down the tube, as I mentioned before, is brought to a focus. Measurements are made down here at the back end of the telescope, where light is converted to electricity through the instruments at the telescope, and then stored, well, sent through a computer and stored with either a tape recorder or a solid-state recorder. The telescope needs to be serviced by the shuttle. Servicing missions have been planned for every 2.5 years, 3 years, to update the telescope, to make repairs for things that fail. And therefore, it has to be in low Earth orbit. And for that reason, it is at an altitude of only about 400 miles above the Earth's surface. That's not a very high orbit. And in fact, it is one of the primary problems that we have to deal with in scheduling the telescope. Any object which orbits the Earth that close to the surface has a period of about an hour and a half. So Hubble Space Telescope is whipping around the Earth every hour and a half. What this means is if you're pointed at any random area in the sky, like it is there, you can see such an object for only roughly half the orbit, because in half of an hour and a half, that is in about 48 minutes, it's a 96-minute period, the Earth will be in the way. And so, by and large, looking at a random area of the sky, Hubble Space Telescope can only see it for half the time. The other half the time, the Earth's in the way, and you have to close the shutter. So this is a difficulty that is a nuisance for astronomers. It'd be nicer if the telescope were in a higher orbit, far away from the Earth, but if that were true, then it could not be reachable by the shuttle and couldn't be serviced. So it's one of the compromises we have to put up with. The data is stored on computer, and then every several orbits, it is uplinked to what is called a TDRS satellite. There are 3 geostationary, geosynchronous satellites, 22,000 miles up, We share those satellites. The TDRS stands for Tracking and Data Relay Satellite System. We share them with the military, with other NASA missions. And about every second orbit, we uplink the data to this communication satellite, which downlinks it to White Sands Proving Grounds. That uplinks it to either Pan Am or Intelsat, downlinks it to Goddard Space Flight Center in Greenbelt, Maryland. They fiber optically cable it over to our institute in Baltimore, which is about 35 miles away from them. That's how we get the data. So we get it in these chunks every 3 or 4 hours. And then we do our thing with it, we process it, we calibrate it, and we disseminate it to our colleagues in the astronomical community throughout the world. NASA has 85% interest in the project, European Space Agency has 15%, but in the United States we have a tradition whereby we accept proposals to use scientific instruments, certainly in astronomy, irrespective of the nation of origin of the investigator, whether or not that nation has any participation in a project. And so, for example, we allow Japanese, Canadian, Australian, ex-Soviet Union scientists to use the telescope, even though they do not have any official participation in it. Well, when the telescope was launched in 1990, it went through a several-month checkout period where everything was brought up and activated. It tried to achieve best focus. And this was the best focus that the astronomers at the Institute were able to achieve with a telescope. This is an image taken with a wide-field camera, wide-field planetary camera, of a star cluster, which contains here in the center over 100 stars here, which the telescope should be able to resolve, but clearly does not. Now, you may not know what to expect of this image, but I can assure you that this looks about like my little 8-inch backyard telescope, if even that, in the sense it is not producing crisp images, and one sees a large halo of light here that is reminiscent of a very poorly focused image. The fact is, this, at that time, $2.5 billion project was found to have what we call an optical mismatch between the primary and secondary mirror. They were not figured correctly. That was a disaster. Here we had something that had been 20 years in development that astronomers have been waiting for to produce all the things it has since produced, and we were left with a seriously flawed telescope. It was a very bad time for the science of astronomy, I can assure you. You could not turn on a television any night without hearing Jay Leno or David Letterman comment on this. And we helped make their careers, and Hubble Space Telescope became a household name because of that. Now, in the same way that Jay Leno and David Letterman arose to the occasion, this situation brought out the best creativity of the political cartoonists that I have ever experienced. And I'm going to show you several of my favorites. Now, I cannot convey to you, actually, the seriousness of the situation. Really, astronomy was devastated by this, and my colleagues and I were devastated. I must say, though, that in spite of that, one must keep one's perspective, and through our tears, I had to laugh hysterically at this. There's more. Now, for those of you who cannot read, this is a countdown that is being halted. And for those of you who cannot see, you should focus on this device over here. And we were subjected to this. It was a bad time. And so what were we going to do? The Space Telescope Science Institute led a study, the community of astronomers, to try to figure out how we could get out of this situation and correct it. There were all sorts of ideas. Bring the telescope, to have a shuttle mission up there, bring the telescope down, fix it on the ground, send it back up. There was a competition. Proposals were received. They were peer-reviewed. And what was eventually decided upon was not to bring it down, because in this real world, we were fairly sure that if that telescope, in its flawed state, ever touched ground, it would never get back into space. And so, since servicing missions have always been planned every 3 or so years, what we decided was we should quickly implement corrective optics, have them in the first servicing mission, have them correct the flawed optics of the telescope. And not focusing, okay, they're supposed to be autofocus, thank you, but I can, of course, it's difficult for me here to, I now realize that maybe I wasn't supposed to take that comment seriously, but I did. I am not in the best place to determine a good focus, seeing it from this angle. So I have to depend upon the good services of you folks. So what was happened was, at the Institute, there was a study that, and a development of some corrective optics that do what you would do to your single lens reflex if it suffered from this same spherical aberration. You know, the lens of a single lens reflex has any number of optical elements in it. And the combined lens, of course, serves to bring light to a focus, but each individual lens contributes to that, but also introduces its own aberrations. And so what the combination of lens does actually is to correct for all those aberrations. One can do the same thing with a Hubble. So what we did was, since there was an aberration in the light as it came to the focus at the back end of the mirror, was we decided to take out one of the instruments and instead stick in several corrective optics in the same way that you would do that to any elementary lens. Do that in the first servicing mission. Light would then pass through or bounce off the mirrors in the corrective assembly and then be brought to a proper focus with these other instruments. So that's what was done, and the device was quickly developed and constructed at Ball Brothers in Colorado, and the first servicing mission that took place in 1993, early December of 1993, onboard shuttle Endeavour blasted off with that as the primary goal. Now, that mission also needed to do several other things because there were some other problems that crept up with the telescope having to do with the solar arrays, which acted like a timpani. They were made of bimetallic material, and as the telescope went from night to day, the heating and cooling as it went through the terminus of the Earth caused uneven expansion and caused a tympanic effect where the arrays kind of popped and caused vibration of the telescope. And so it was impossible to get good images out of that, in addition to the problems of spherical aberration. So there was a crew of 7 astronauts in that first servicing mission that really performed superb work in doing all of this, demonstrating that people could work in space and correcting the flaws of the telescope. I'm going to show you several slides from that servicing mission. Here is Hubble right after grapple over one of my favorite places in the world. This is the southern cone of South America, where my wife and I were in fact working in Chile, where we lived for 8 years before we came up to Baltimore. But here you can see the solar arrays of the telescope right after it had been grappled. These had to be jettisoned because they're in the way before work could begin on the telescope. And then there were a series of 5 what are called EVAs, extravehicular activities, or spacewalks, that were undertaken to make the various change out of the solar arrays and the instruments at the back end of the telescope. There were 2 teams that did this in alternating spacewalks. This is Story Musgrave and Jeff Hoffman, about to commence work on the first spacewalk, where they were going to change out, this is the third spacewalk, where they're going to change out one of the cameras in the back end of the telescope. Here is either Story or Jeff with taking out the old wide field camera before putting in the new one. It has the size and shape of a grand piano. Very heavy, but of course, in a weightlessness in space, in orbit, it was very easy to move it around. Here they are on the same orbit, inserting, except on the dark side of the Earth, inserting the camera in the telescope. These spacewalks had to be very carefully choreographed because various things expand and contract on the telescope, and depending upon the work that they had to do, they either need to have light or they could do it in the dark. And so it was, all of the spacewalks were really very detailed and had to be executed to a very precise timeline. But in fact, they ended up doing superb work. Here's another the spacewalks. The second team was Tom Anker and Kathy Thornton, and here they are up against a telescope about to do some of the work. There are a bunch of yellow handrails around the telescope, about 100 of them, that are there expressly for the astronauts to hold on to while they do their work. Talking to them, there are very interesting things that they experienced on these spacewalks. One of the things is apparently a fear of falling. It gets very dark when you're on the dark part of the Earth. And there is a light, like a miner's lamp on their helmets that enables them to work. But the fact is, if they happen to point their head such that that light shines out in space and it doesn't reflect off the telescope, because on the dark side of the orbit, the people inside the shuttle need to see them working out there. They turn off all the lights. It is extremely dark up there. And on the most recent servicing mission, there's been two now. There's one a year ago, February of '97. Astronaut Mark Lee, who was in one of the spacewalk teams, told me that he had this fear of falling all the time that he was working in the dark. And it impeded his ability to do the work because even though, of course, you're floating with a telescope, and even if you did nothing, you would not move with respect to it. He could not get over this instinct of falling toward the Earth. And so he found himself continuing to grab onto one of these rails. Well, first of all, it impeded what he had to do, and he found near the end of one of his spacewalks, which lasts for 6 hours, that his arm started cramping up. And they almost had to end that particular spacewalk because of that problem. So very interesting things. The astronauts always report very vivid dreams when in their sleep, when they're in space. And another thing that they experience is a very high number of cosmic rays. Cosmic rays are elementary particles, like protons and electrons. They have very high energy. They exist throughout the galaxy, and particularly the solar system, because many of them come from the sun. And the Earth's atmosphere protects us from most of them. It impedes them, but when you're above the atmosphere, they pass through your body. And they can do bad things. They can cause genetic mutation. And so there is a period or a position over the South Atlantic where the Van Allen belts happen to dip down close to the Earth's surface. It's called the South Atlantic Anomaly. That is a region where one is subjected in low Earth orbit to a very high particle rate, and the astronauts cannot be outside the space shuttle at that time. So the timing for all the spacewalks, when you see astronauts going through the spacewalks, is such that they must be inside the space shuttle when the orbit passes through the South Atlantic Anomaly. 6 out of 15 orbits every day do that. So there's only a precisely defined window where they can be outside the shuttle. And even then, it turns out their eyes are cosmic ray detectors that are quite efficient. And some of them report the yellow scintillation in their eyes that is so strong when they're sleeping that it wakes them up. And it tends to have this yellowish color. There are all sorts of stories like that, very fascinating in this otherwise hostile environment. Well, on to science. This is separation of the telescope with the new solar arrays. Right after it had been released, the high-gain antennas once again deployed, and telescope ready to work. This is one of the more beautiful shots of the telescope that was taken not on that first servicing mission, but in fact in the second servicing mission a year ago. And I show it to you just because of the beauty of seeing the shiny telescope against the blue atmosphere of Earth and then the dark of space above it. Well, This is a result of the images that resulted after that fix. Here is an image of a group of stars taken from an excellent ground site, a ground-based telescope in Hawaii. Here is what Hubble gave us before, with the spherical aberration, before it was serviced. You can see this terrible halo here that still produces better images than you get from the ground. And here is what the telescope is producing now. It is essentially giving images as good as one can get. We sacrificed 4% in the throughput. That is, the telescope is receiving light with an efficiency of 96% of what it should be doing. This is with the corrective optics. So away we go. Here's a comparison of a star cluster before the servicing mission and after. You can see that detestable spherical aberration is now gone, and you can resolve these stars as they are supposed to be resolved. Now, I want to describe the science that has come out of the telescope in this state, but before I do, I would like to comment on some interesting applications that have come from the research that was done with the telescope when it was in this flawed state. Because this image of a star cluster right here is reminiscent of this image right here that has nothing to do with astronomy, but in fact is an X-ray of the female breast. It is a mammogram. There has been some very interesting research that came out of our institute and Goddard Space Flight Center where software was developed when the telescope was producing spherically aberrated images that has excellent application to radiology and the detection of precancerous microcalcifications in the female breast. And it turns out that the software we developed is making mammography much more reliable because of that. The job of a radiologist is to take an X-ray like this and look for what are called microcalcifications, little nodules down here that may be precancerous. Now, it's a difficult job because the female breast is not flat, okay? And therefore, in an X-ray, you find regions that are underexposed to overexposed. And not only that, breast consists of tissues of different density, fluids, and the like, and therefore you have a very uneven background. So you can see it's very difficult to make such a detection using the naked eye. Now, what we did at the Institute was to develop software very similar to trying to study a star with a spherical aberration that would get rid of the background image and enhance starlight. Well, the same thing is true of microcalcifications here. And this gives an example of what happens if you take the X-ray and you digitize it. That is, you put it on a machine that converts the actual X-ray, the photograph, to an electronic file. What you do is you create a very fuzzy image of the breast or the X-ray right here, and then subtract this image electronically from this image. What that does is produces this image down here. It gets rid of what we call the large spatial scales. That is, it produces a uniform background while preserving the small structure that in fact is a microcalcifications that the radiologist is looking for. If you then take this background, this uniform background, and subtract it out, or in jargon, pass an adaptive filter over it, what you're left with is this lower right-hand image. This is what the radiologist can now look at, that basically are the microcalcifications that are hidden in here in this tissue. Much easier to make a detection here than here. This is particularly important because as the female breast ages, it naturally develops microcalcifications. They are not precancerous. And therefore, one has to distinguish between the precancerous and the benign microcalcifications. One does that by looking at the clustering tendencies. Normal benign microcalcifications have a certain size distribution and they tend not to cluster, whereas precancerous ones tend to cluster. This is a very dangerous one that would indicate a biopsy. In fact, National Science Foundation finished about a year ago funding the Institute and the Vince Lombardi Cancer Center of Georgetown University in Washington, D.C., in a study where we applied this to mammography, and it turns out that the results of that study, which are now out, indicated that it was very effective in enhancing improving the reliability of mammography. During the study, we found a number of false positives and false negatives that really affected the diagnosis. So an interesting situation in which pure research led to some very important practical applications, and who could have known this before we started. A very good example of the importance of supporting basic research. All right, let's work our way out in the universe, starting with the solar system and ending up at very distant galaxies. This is Mars. Hubble doesn't look very often at the planets. And the inner planets toward the sun, Mercury and Venus, it almost never looks at them. The reason for that is sunlight cannot be allowed to penetrate in the tube of the telescope. For the same reason that if you leave your parked car with the windows up in the sun for a couple of days, what you find is you come back and you notice there's this thin white film on the inside of your windshield. That would happen to Hubble telescope if we let sun, even for a few seconds, hit the inside of the tube. What would happen is there would be outgassing at the inner part of the telescope tube. Polymers would form. They are attracted to any smooth surface, like a telescope mirror, and that would coat the surface and cut down on its reflectivity. So we do not look toward the inner part of the solar system. Mars basically is the closest planet that we can look at, and some very interesting results have come out actually from Hubble images of Mars. Mars has turned into a refrigerator, an icebox, in the 20 years since the Viking 1 and 2 landed there. This was first discovered from ground-based telescopes and has led to this, what now is sort of a permanent fixture on Mars that was not there 20 years ago, and it is this blue haze around the edge of Mars that is basically the formation of ice crystals from H2O that comes from sublimation of the polar caps. The surface temperature of Mars is now almost 40 degrees Fahrenheit less than it was 20 years ago. This is an amazing fact. I mean, when you consider that we talk about global warming on the Earth being a change in temperature of the Earth of 1 or 2 degrees, the entire surface of Mars is 40 degrees less in 20 years. On Earth, obviously, this would wreak havoc. It would also be impossible to achieve without some fundamental change in the sun. And the sun's light, radiation, has not changed in that time. So what has caused this? Sorry, I can't give you an answer, but I can. The fact that it is possible on Mars is due to the fact, two things. First of all, Mars does not have oceans now, and the Earth does. The Earth has these huge thermal reservoirs, which are oceans, which trap tremendous amounts of heat that would cause surface changes of this magnitude on Earth to be impossible. Mars also has a very insubstantial atmosphere. And so the fact is, it is not that difficult to bring about large changes in the temperature on the surface, and it is believed that some severe dust storms, there have been 3 very prominent dust storms in the past 20 years since Viking landed that caused increased reflectivity of sun's light back out into space, prevented the sun's light from reaching the surface, that is believed to have contributed to this effect. Nevertheless, what happens is one finds for about an hour and a half as Mars turns here left to right, you constantly see, and can even be seen from ground-based telescopes now, this blue haze that basically is the ice, which eventually evaporates during the day and then starts to form again as you get to the night time on Mars. Very interesting effect. There are some interesting studies of Jupiter and its Galilean satellites. One of which is a satellite called Io, has a size about the same as the Earth's moon, and is really interesting because it undergoes volcanic eruptions, and there are volcanic flows, highly sulfuric, which leads to this yellowish appearance here. Now, space probes 20 years ago first saw these volcanic flows. but they are long gone. And apart from the Galileo probe, which is there now and which can study them, Hubble is an excellent instrument to be able to chart these things. One actually can see the surface of a satellite of Jupiter and chart the changes in the volcanic flows. This is a fairly recent image from the telescope that captured, several months ago, a very large volcanic eruption that spouted material up 250 kilometers above the surface. That is a gigantic volcanic eruption. And these dark flows have been observed with the Hubble to actually change from year to year. So we're actually seeing the surface of this satellite undergo changes. The fact that Io is volcanic is very interesting, because one would not expect something that is as small as Io, considerably smaller than the Earth, to have a hot interior. The Earth has volcanic activity because it is large enough to trap heat produced by natural radioactive decay, U-238, potassium-40, underneath the surface. The reason that Io is molten inside is due to something that most of us find amazing, and that is the gravitational tides. Very strong gravitational field from Jupiter actually distorts Io, which is not in a perfectly circular orbit. And over a several-day period, as Io moves around Jupiter, torques the planet in such a way that it heats it up. It raises land tides on Io, and that effect has actually heated the interior of the satellite and is what produces this volcanism. This image, Io is here seen against Jupiter's surface. So here is Jupiter, very beautiful photograph. A few years ago, well-known impact of a comet which was orbiting around Jupiter and got progressively closer to the planet until tidal interactions actually broke it up into about 25 individual fragments, each having a nucleus of about half a kilometer. And in 1994, these actually were on an orbit in which they collided with the planet Jupiter. Each one of those fragments moving at 50 to 60 kilometers a second, plowing into the planet. Unfortunately, that collision occurred on the backside of the planet, and so we couldn't see it. And to observe it, we had to wait until Jupiter turned, because it rotates every 10 hours, and then have the collision sites actually brought into the Earth's view. Here is a montage over a 20-minute period where you see a Hubble image taken of the limb of Jupiter right at the time of impact, and then 3, 6, 13, and so on, 20 minutes later. And you can actually see the mushroom-shaped cloud that this one fragment raised on Jupiter, and then you see this stuff settling down into the stratosphere. Jupiter. Really amazing phenomenon that astronomers were aware of happened, but we never had any expectation that any of us would actually be able to observe this phenomenon in our lifetime. Here's a very nice montage, color images taken of the impact of one of the fragments. This was about 5 minutes after it impacted. You see the mushroom-shaped cloud here rising up above the limb of Jupiter. The impact actually occurred in the backside. Several hours later, when the rotation of the planet brought that impact site into view, and then several days afterwards. And you can see that the winds on Jupiter actually caused a distortion of the impact site such that it was drawn out in this elongated pattern after a period of some days. I should say that measurements from ground-based telescopes showed that this spot here achieved in the hours after the impact a temperature 20 times greater than the temperature of the sun. So it was hot. It was large. This circular image right there is the size of the Earth. So Jupiter is much larger than the Earth. One can therefore imagine what would happen if this comet had not hit Jupiter, but had hit the Earth. It would have killed the dinosaurs. An interesting illustration of the fact, we look out there at night, you see this beautiful universe. The fact is, it is a violent laboratory. and producing really interesting results. This was a fascinating thing to behold. My last solar system slide is an image of Pluto. This is computer enhanced. Here is the raw image taken with Hubble. And the reason I show it to you is because to some of us, this is an amazing photo. When I was a graduate student, it was not known that Pluto had a satellite. We now know that. And the size of Pluto wasn't known. Even within factors of 2 and 3. Now with Hubble, not only do we have an accurate determination of the size of Pluto, we are able to see very crudely surface markings, probably due to ices on Pluto because it is the most distant planet in the solar system. Again, not much we can say about it. We know it's cold, but the fact is this is a good illustration of the advances that telescopes like Hubble have brought just in my professional lifetime. Because when I first started giving lectures as a professor at the University of Arizona, I talked about Pluto. Much of what I had to say was guesswork. So this represents tremendous progress. Well, let's work our way out. All Gaul is divided into 3 parts. The universe is divided into 4 types of objects. Almost everything that you see out there can be classified as either a planet, a star, a gas cloud, or a galaxy. And if there's nothing else you take from this lecture, other than that and the fact that Hubble Space Telescope is worth funding, then you've learned something. And the fact is, this is an elementary astronomy course, right? You have a good understanding of 2 of those 4 types of objects. Planets, we understand. We live on one. The stars, we understand something about because we're fairly familiar with the sun. So there's 2 out of 4. We're going to talk now about, the rest of the lecture, about gas clouds, the 3rd constituent, and then about galaxies, the 4th constituent. And hopefully give you a feeling for what these things are. This is one of the most famous gas clouds in our galaxy called the Orion Nebula. Big gas cloud. Some light years in size that is in the constellation of Orion. It's beautiful. That's not why I'm showing it to you, but that's a good reason. It turns out that these gas clouds are intimately involved in the life cycle of stars. Stars don't just exist for all times. They were always there and they'll always be there. Stars are like people. They're born and they die. They evolve. And these things are essential to the evolution of stars, and they are what I would say is the carriers of the genetic code in the universe. Stars form out of these things. They emit light by nuclear reactions converting hydrogen to helium, and when they exhaust that fuel, they collapse and they blow up. And they form other gas clouds, out of which new stars form. So there's this life cycle of star, cloud, that goes on inexorably. And the net result of that cycle is to take simple elements which were prevalent in the early universe, read a little book about the Big Bang by Professor Craig Hogan, and convert that to heavy elements. And this is important because the heavy elements are essential to the formation of life as we know it. Life could not form with just hydrogen and helium, and so that's why I say these things are the carriers of the genetic code. This is one of the most prolific maternity wards in the galaxy. There are hundreds of stars forming out of this huge, immense gas cloud. They've been imaged by a colleague of mine at Rice University, Bob Odell, and this is a close-up, a detail of one of the 115 stars that are visible actually in that previous image. And the interesting thing about them is that fully half of those over 100 stars do not have a spherical shape. Now, we're familiar with the sun, it's round. We know why it's round, because of its gravitational attraction. If you take a fluid and it's not spinning too rapidly and you subject it to its own gravity, like the Earth, it'll form a spherical shape. Half the stars that one sees with the Hubble are not spherical. They have this oblong shape. This is probably the best example. Looks like a disk. There's a disk here that is seen darkly. That is because this star, it is what we call a protostar. It's a star that's very young, not yet formed, still collapsing, so it hasn't turned on. So what we see is the obscuration of this thing, and it looks like it has a disk shape. It appears that the formation of stars leads to this disc-shaped structures, which we expected actually, but had never before seen, and we believe are intimately related to the formation of planetary systems. Hubble cannot see individual planets. It's going to take a bigger telescope than Hubble to do that, but we believe that the disk shapes are indicators of planetary systems, and with subsequent space missions involving larger telescopes, different instruments, we hope to be able to see them. But the fact is, we have always suspected from theoretical grounds that the formation of planetary systems was a very common phenomenon in the universe. This appears to be supporting that evidence. This is another gas cloud, the most famous picture the Hubble has taken by far. It is called the Eagle Nebula. It is at a distance of some thousands of light years away. You see these three pillars or columns of dust and gas that exist here. And the first time I saw this image, I was amazed. I was quite taken by it, because never before have any of us seen an image that looks so three-dimensional. We're used to seeing images, but most of them look two-dimensional. This image just looks like it's three-dimensional. Why? Hard to say. Maybe the backlighting that you see here. Here's this veil of material, and you can see through it. Here's this thing that looks like a worm or a caterpillar or E.T. or whatever. I mean, it is an amazing object. This structure had been seen from the ground, but not in the detail that you can see it here. And actually, a very interesting physics going on here also, because the secret to understanding this image lies in some very hot stars, a couple of hot stars that are way up here that you can't see, that are shining down on this thing and heating it up and evaporating it. Now, there are a bunch of fingers that you can see here, isthmuses, if you like, that all are oriented in the direction from the lower left to the upper right. They're pointed in the direction of these hot stars. There's a little one right there. There's some over there. What is happening is, out of this huge giant gas cloud, stars are forming. The stars are producing a shadow from the light of these hot stars that protects, basically, the material behind it from heating up and evaporating. And so these hot stars are evaporating away this huge column of gas, except in those regions where you have stars forming here, right at the tip of these sort of little, fingers. And hundreds of thousands of years from now, what you're going to be left with is all this gas evaporated away, and these stars, which will have turned on and start shining by then, and these little fingers, which will then evaporate away. So a really beautiful image. And another illustration of the activity that is going on out there in space, the formation of stars. Here's a detail of that. I mean, really, you can just see the gas seething here. You can imagine it. It really does look like some living object, some giant worm. In fact, it isn't. There are many interesting shapes that exist, preferred shapes that exist in the universe that gas clouds assume. And one of them is formation of disks. Here you see one edge on, as if you're looking at my hand, right along the plane. And then what are called jets. A jet is a collimated, a pencil beam of gas, and you see that in the reddish color in these three objects here. There's nothing artificial about this. In fact, I should say that every photograph that I'm showing you that I am aware of is true color, with the exception of one. And I'll try to remember to point that out. So these are real colors here. We do our best to give faithful reproduction of the color. But here you see some gas streams moving out in a line. These are the centers of these objects are young stars that are forming, and it is an interesting question of what it is that is producing these collimated beams of gas that are being produced by this ejected gas. Really pretty to look at, and interesting to study physically, because we're still not certain why it is, what physical processes keep the gas so aligned or focused so well. This is the false color photograph that I just mentioned to you. This is not the actual color of this object, but there are two types of gas clouds. Gas clouds that are out of which stars are forming, and gas clouds that are produced when stars end their life and blow up. And you've just seen some of the large examples of the maternity wards or birth places where stars are formed. Here is an example of a dying star that has wafted off its outer layers, and produced this, what is called a planetary nebula. This is a gas cloud, not as large as the previous one, but you see an interesting symmetry here in this explosive phenomenon. I'm going to show you several pictures of exploding stars because some of the neatest images of Hubble are images of exploding stars. This is, again, amazing object in the southern sky called Eta Carina, a star that underwent a sudden brightening 1.5 centuries ago, 150 years ago. Astronomers didn't know what it was. With ground-based telescopes have seen sort of a fuzzy object, and here with Hubble, you see this bifurcated, two lobes. It looks like two brains almost, but it basically are two expanding clouds of gas and dust that you can see with all this beautiful structure here. Really a marvelous object. Here is another. This is called the Hourglass Nebula. Again, an exploding star, exploded about 10,000 years ago, did not completely disrupt, but produced this beautiful wispy sheet of gas. I'm going to show you several objects that look like this and can be understood if you perceive this as an hourglass-shaped object that you were seeing at about 45 degrees angle. Here is the top half of the hourglass. Down here is the bottom half of the hourglass, seen at an angle, and here is the waist of the hourglass. And there is a star down here that blew off material that produced this. You see a very interesting symmetry here. And in fact, astronomers are studying this are not exactly sure what produces this symmetry, but one thing we can say is that the gas that has been blown off in this star is enriched in complicated elements. I mentioned this cycle, this mutation that stars do to the elements of the gas out of which they form. They take the hydrogen and convert it to helium, the helium and convert it to carbon and nitrogen and oxygen and more complicated elements. We are actually seeing that because if I can go in reverse here, in the gas clouds like these that stars are forming out of, we see them to be predominantly hydrogen and helium. But in these explosive gas clouds like this, they are much more enriched in elements more complicated than hydrogen and helium. And so this is this mutational cycle where elements are gradually being converted to more complicated species, something that is absolutely essential to the formation of life. Here's the last gas cloud I'm going to show you. Again, another structure that looks like the hourglass. This is a supernova, a star that blew up that we first saw about 10 years ago. And you can perceive as this hourglass shape. Here's one hemisphere, this ring. Here's the other hemisphere. And then this elliptical shape here is the waist of the hourglass. So very interesting phenomena by which stars blow off material and do so in a manner that produces this beautiful symmetry. As if magnetic fields or something were producing were effective in producing the shape, although we think that probably is not really the reason. We're not sure what it is. There are various theories. Well, let me finish up by talking about the largest structures in the universe, galaxies. If you look out right now in space around us, you see galaxies. It's very difficult to see them with the naked eye. There's only several galaxies that are bright enough to be seen with the naked eye, but through even a moderately sized telescope, you can see a number of them. And if you were to look at galaxies, you would, by and large, notice that they come in two shapes. They are either spiral, like this galaxy, which looks a lot like our own Milky Way. They have a nucleus of stars. This galaxy fundamentally consists of a few billion stars that are all held together by their own gravity, and they are moving around in a spiral pattern. Such galaxies are called spiral galaxies. The other type of galaxy that one sees at the current epoch in the universe is called an elliptical galaxy. They tend to be these amorphous concentrations, again, of billions of stars that are basically spherically shaped or sometimes somewhat elliptically shaped. Some of the fundamental concepts in astronomy, important really in the 20th century, come from the study of these galaxies. The first concept is, first of all, the realization that other galaxies exist, because the existence of other galaxies was not known until the 1920s, in this century. Prior to that time, these fuzzy objects that were seen in telescopes were believed to be simple gas clouds in our own galaxy. So the existence of other island universes or other galaxies was not known until 75 years ago. That's one important fact. The other important fact that has emerged just in the past generation is the fact that although we're seeing billions of stars in this ensemble this galaxy, this ensemble of stars, we are actually not seeing most of the material that is contained in that galaxy. And most of the material there is invisible, so-called dark matter that we cannot see. Now you may ask, how do you know what's there if you can't see it? And the answer is, one infers its existence from circumstantial evidence because of the effect it produces on the stars that one does see, the gravity. It turns out that all these stars are moving around each other, passing through, mostly without colliding, because although this looks like a huge swarm of stars that would collide with each other, most of what's here is really empty space. And one can determine how much material, seen and unseen, is in this galaxy by measuring the motions of the stars. And it turns out that there is much more material here that is invisible than there are stars that we see. Again, amazing fact that applies to most galaxies we look at, and therefore we astronomers deduce that most of the material in the universe is material that we can't see, and therefore whose nature we do not know. It could be bricks, it could be dead planets, dead stars, small little grains of sand, astronomers call dust, black holes. It could be virtually anything. And one of the really interesting areas of investigation in astronomy the past 2 or 3 generations has been our attempt to determine what is this stuff that we know exists there but we cannot see. Well, it could be black holes. We think it's probably not primarily black holes, but that possibility merits some attention, and so I want to describe some of the interesting research that Hubble has come up with on black holes. A black hole is a dense concentration of material whose gravitational attraction is so strong that near its surface, light cannot escape. That is, it has what's called an escape velocity that's greater than the speed of light. Truly black, can't be seen. Now, if black holes cannot be seen, again, you ask, so how do you know they're there? And the answer is circumstantial evidence. You're walking along a river, heading up toward the mountains. The trail takes a bend. You see water flowing down. You hear a roar. You see mist. You deduce there's a waterfall, even though you don't see it. Same is true of black holes. We cannot see them, but we can infer their existence through the circumstantial evidence that they leave behind, their footprints. What is the footprint of a black hole? It is believed by physicists and astronomers to be this. It is believed, here's a black hole down here, that one can infer the existence of a black hole by its effect on the material that is around it and material which may be falling into it. Heated up to glow. In the same way that when you pull a plug in a bathtub, water goes down the drain pipe, circles around the drain because of a property that's called angular momentum, because of its motion. The fact is, if material happens to be passing near a black hole and is pulled down toward it because of its strong gravity, we believe it will form a disk, it will heat up, and then calculations indicate that one of the manifestations that one would expect is not just the disk, but these collimated streams of gas that emanate from it. And so if you want to look for a black hole in space, you look for this. Question is, have such objects been seen? And the answer is yes. Not only Hubble, but some radio telescopes now have unambiguously found evidence for the existence of black holes in the centers of galaxies. And this is one of the best examples. This is that same galaxy that I showed you 2 slides ago, except taken in different type of light, filtered light. Here is a very large jet that in fact has a length of thousands of light years. Quite impressive. The number of miles is 1 followed by a whole bunch of zeros. Thousands of light years in length. Collimated beam of gas, material that is being ejected from the center of the galaxy. So that's one of the things that one looks for in looking for a black hole. Now the question is there the disk that one expects, one that is rotating very rapidly because of very strong gravity that one associates with a black hole? And the answer is yes. Holland Ford, a professor, collaborator, colleague of mine at Johns Hopkins University in Baltimore, used Hubble to image the center of this galaxy down here from which this collimated gas is being ejected. And he found a disk of material, and he was able to measure the speed of found out that the gas was rotating and was able to determine what the speed was. He found it to be so high that in fact one must have an extremely dense concentration of material down at the center of this thing. It must be a black hole. And there are about 9 or 10 other objects that Hubble has imaged that have the same configuration. The evidence does appear to be very strong now, almost overwhelming, that black holes reside in the centers of many galaxies. So that may be, in fact, it must be part of the dark matter that exists in the universe. We suspect it is not all of it, but it is certainly interesting for you to realize that this theoretical construct called black holes now is at the point where we believe very strong observational evidence exists for their existence. Okay, final series of slides. I was talking about important concepts of the 20th century that have come from astronomy. Perhaps the most important has come, and is one that Edwin Hubble was involved with, has come from the study of clusters of galaxies. This is a ground-based image of a cluster of galaxies. Each one of these fuzzy blobs consists of some billions of stars held together by their gravity. One of the things that Hubble determined was that clusters of galaxies are all spanning away from each other. Wherever we look, they all are moving out. If you take this concept and project back in time to what the universe must have been like earlier, then one comes to the deduction that all these clusters of galaxies must have at some time been much closer together and in a much denser state. This concept, which Edwin Hubble had so much to do with, has given rise to the concept of the expanding universe and the fact that all of this material must have been in an extremely dense phase at one time. The universe had an origin. And that origin must have been in a very dense and a very hot phase, because when you take a gas and you compress it, it becomes hotter. This has given rise to the concept of the Big Bang, the beginning of the universe, one of the really important concepts of our time. And it is Hubble's ability, Hubble telescope now, not astronomer Edwin Hubble, passed away in the 50s. It is Hubble telescope's ability to image distant galaxies that I believe will be its enduring legacy. Now, astronomers want to understand how galaxies form and evolve, and we have a problem, because unlike stars, which are forming and they're dying, they're going through their evolution in front of us at all times, galaxies do not do that. for whatever reason, galaxies seem to have all formed long ago, near the time of the Big Bang, which is roughly 15 billion years ago. And so if we want to understand how these things came into being, we need to look back at a time when it happened. Well, astronomy provides that, because the finite light travel time, the finite speed of light causes there to be a delay in the time for which you observe an object and the time the light actually emanated from the object. We're looking at the moon as it was 1 second ago, because it takes the light 1 second to get here. We're looking at the sun as it was 8 minutes ago, because it takes light 8 minutes to travel between the sun and the earth. The more distant you look out in space, the further back in time you look. And so if we want to look at galaxies at a time when they formed billions of years ago, if we can look out at a distance of billions of light years, we can actually see those galaxies as they were forming at that time. Hubble Space Telescope, with its clear vision now, enables us to do that, whereas previously from the ground we could not do it. And there's a series of pictures now that I want to end with that really show Hubble at its best, where astronomers have looked out at successively further distances in order to see galaxies at the earliest stages and get as close as we can to the time of the Big Bang, when presumably these things formed. The first image is one of a cluster of galaxies that was one of the first images taken after that first servicing mission that fixed the telescope. Here you see a bunch of galaxies that happen to be at a distance of 5 billion light years, a tremendous distance. Remember, 15 billion years ago, roughly, was the time of the Big Bang. So now we're a third of the way back to the Big Bang, looking at galaxies as they were at that time. This is a montage of galaxies that appeared in that last slide. What you see are galaxies actually that have a shape that looks fairly much like the spirals and elliptical galaxies that we generally tend to see around us now. These are all elliptical galaxies, these fuzzy blobs. And so these galaxies look like elliptical galaxies at the current time. And down here you see some roughly spiral-shaped galaxies like the Milky Way, although they show some interesting differences. Some of them have 3 spiral arms. Some of them have more than one nucleus, apparently. Some of them have prominent rings. But the fact is, these are roughly spiral galaxies. If you ask me to classify that galaxy, I would say that's a spiral, although it doesn't quite look as regular as spiral galaxies nowadays. The point is, 5 billion years ago, it looks like galaxies were not quite like they are now, but pretty much the same. Let's go out further. This image was taken a year after the first servicing mission by a colleague of mine at the Institute, Mark Dickinson, who I work with. This was in 1994. This is a system of galaxies that is 9 billion light years away. And the detail of some of these is shown here. There's a cluster of galaxies here that shows elliptical systems, and I think I've got a montage. I don't have a montage, so let me go back here. You don't see any spiral galaxies. Instead of spirals, you see what Mark has called garbage galaxies, or train wrecks. Totally dysmorphic, asymmetric galaxies. The ellipticals are here, but no spirals. It looks, therefore, 5 billion years ago, you see spirals. 9 billion years ago, you don't. Now, it could be that we're not looking at a typical spot in the universe. We need more data. And so, several years ago, some of us at the Institute decided that what was needed was an extremely long exposure of a typical region of the sky that would enable us to burrow through the universe to see all objects to as far as we could see in a reasonable period of time with a telescope. And this image, which is called the Hubble Deep Field, resulted from that. This is an image which, if you were to look with ground-based telescopes, only contains a few of the brightest galaxies that you see here. Most of these faint galaxies have never been seen before and represent very distant, for the most part, galaxies. There are a few stars in our own galaxy that this image contains, like that and like that, but for the most part, most of these faint objects represent galaxies way back at a time when the universe was young. And in fact, there are some really curious shapes here. This is my last slide, and is a detail of those galaxies that you see in the Hubble Deep Field. Some of the nearby brighter galaxies have this spiral shape. There's a spiral, there's a spiral. But you also see some really strange looking things here, like this. We call that the hot dog for obvious reasons. We got other names for this, not quite like the Martian rock Scooby-Doo and Barnacle Bill, but the fact is we have named. Some of these galaxies have been measured to be at a distance of about 12 billion light years. And they have very strange shapes. We are now studying them. And the exciting thing about this particular image is it is the deepest core sample that has ever been taken in the universe. Yes, there are some nearby stars and nearby galaxies in it, but the fact is it gives us a great sample of some of these really distant galaxies that we can now study that we've never before been able to do. Well, this basically takes us to the limit of the capabilities of the telescope as it is now equipped. And I think you can see that it provides us with the ability to understand some things that astronomers have been wanting to do for a very long time. As exciting as this image is, I think that the real significance of images like this and what the telescope is producing is not so much this, but the fact that if you understand all of this material in terms of this evolutionary cycle that I was mentioning, where gas clouds form stars, they blow up and form other gas clouds out of which subsequent generations of stars form, what we are seeing in this image is our own origins. There was a well-known astronomer early in this century, director of Harvard College Observatory, his name was Harlow Shapley, who referred to this situation by saying that we are all brothers of the boulders and cousins of the clouds, because we evolved on this earth from material that was near the surface of the earth at that time, which in turn came from material out of which the sun formed, which in turn collapsed from a gas cloud that had been there, that had gone through this cycle a number of times. The fact is, we know when we look out at these most distant galaxies that we're seeing predominantly hydrogen and helium. We know, though, that a large fraction of our bodies contains elements that are more complicated than that. In fact, most of our bodies are water, H2O, a lot of oxygen. That oxygen does not exist in those most distant galaxies. It had to have been formed out of this evolutionary cycle involving the formation of stars. For this reason, we really are brothers of the boulders and cousins of the clouds. We are really looking at our origins when we see an image like this, and that really is the significance of the data that Hubble Space Telescope is sending us. And it is that message that I leave you with tonight. Thank you very much.